Hello. So in this chapter, we are going to see mainly PPO, proximal policy optimization, which was for a long time the state-of-the-art algorithm for continuous control problems, at least until TD3 was published. And that's a very important algorithm to understand. We will see that it's used, for example, by OpenAI to play Dota against humans. That's a very central method. The mathematics are a bit complex. We need to use natural gradients, although we won't talk about it that much. And it's based on an earlier version of PPO, which is called TRPO, Trust Region Policy Optimization. So we are going to talk about what a trust region is, and that will allow us to understand the PPO. So we have seen until now two classes of algorithms, the off-policy and on-policy algorithms. So DQN and DDPG were examples of off-policy methods, and they had the main advantage that we could use a replay memory, so reuse past transitions to train the value network or the policy network, depending on the algorithm and their variants. So one advantage of this replay memory that because they reuse past transitions, they don't need as many new ones. So they are more sample efficient. They need less transitions to converge to a good policy. But the problem with being off policy and using these older experiences is that the critique can be biased. And in Q-learning based methods, we have seen the main problem is overestimation. So the critique may be wrong because it's evaluating past transitions. So there's a bias which is used by the actor to learn, and learning can become unstable. So we have a policy collapse, we will explain that again. And the policy you converge to may be suboptimal, so not the best one you could have achieved. So they are faster but worse in terms of the policy you obtain. On policy methods, such as A3C or any actor-critic architecture, at the exception of DDPG, we cannot use a replay memory because we need to learn from fresh examples every time. So you have to act and learn at the same time, and you cannot rely on the past like with replay memory. So we saw that we had to use distributed learning, means I have different actors working in parallel, gathering transitions with the current policy, and then there's one learner network that learns from these transitions and sends weights back to the actors. So because you are acting on policy with fresh examples, you are less biased, so the values that you learn are less biased, and so you can learn better policies. So the policy learned by actor-critic or on-policy architectures is usually better than with an off-policy method. But of course, because you don't reuse the past, you need a lot of transitions, and that creates a sample complexity. You need to interact a lot with the environment in order to learn that better policy. So that's two sides of the same coin. Either you don't need that many samples, but the policy is bad, or you need a lot of samples and the policy is better. One common problem to all these methods is called parameter brittleness. That means they are really tricky to train. So the hyperparameters that you choose will determine if you converge to something correct or not. And that's also true for on-policy. This statement is true only with the right hyperparameters. That's much more difficult than in supervised learning, where the hyperparameters have an influence. But if you change your learning rate, for example, from just a little bit, it's still going to converge in supervised learning. Maybe you lose 1 or 2% accuracy, but it's not as dramatic as in DRL, where if you use a learning rate of 10 to the power of -5, you may find a policy, but if you just use 1.1 times 10 - 5, it's not going to learn at all. It's really sensible, and you have a lot of hyperparameters that influence the success of learning in all DRL methods. For example, how big should your replay buffer be? How often do you update your target networks? If you don't train the actor in the critique every step, what is the ratio that you use? And all that is going to influence a lot the results that you obtain. That's a huge issue, and the idea behind PPO is, can't we do better? Can we try to take the best of both worlds, trying to make an algorithm which is both optimal and sample efficient? It's not true, but at least it will be better than the state of the art. So where is the problem with on-policy methods? Why are they so slow? Problem is that the true policy gradient, what we use to train the actor, is defined by this, the expectation of our transitions taken by the current policy, or the gradient of the log of the policy, times the true Q value of the action. It's really the Q value under the current policy. But what we do with an actor critique architecture is that we estimate this true Q value with another neural network, the critique, which will be an approximation of the true Q value. But of course, because we are using neural networks, there will be an error, a bias in the critique. And if your bias is too strong, that will impact the gradient that you pass to the actor, and learning may not work. And this explains why we have to be on policy, because in order to have a correct policy gradient, we need really good Q values. So the transitions which are used to train the critique must be close from the transitions that would be generated by the current policy. If you're training the critique on transitions that are not chosen by the current policy, then you are going to introduce a bias in these estimations, and that's going to destroy your policy gradient. It will become biased, and the actor may not converge. So it's really the same policy that must be used to train the critique. You cannot sample from a behavior policy like in off-policy methods. If you were to do that, sample transitions from the behavior policy, you will need to use importance sampling, as we have seen in Monte Carlo methods, by correcting the policy gradient with the importance sampling weight, which is a ratio between the probability of selecting an action under the current policy and the probability of taking that action with the behavior policy. So that's possible in practice. You always have the right to do this. That's called an off-policy actor critique, off-PAC algorithm, where you simply use importance sampling to correct the policy gradients that you estimate using a behavior policy. So it's Degree and colleagues in 2012 that proposed this algorithm. If you forgot what importance sampling is, please have a look at the Monte Carlo lecture again, because we are going to use importance sampling a lot in this section. The problem is that off-PAC only works with linear approximation, so not with a deep neural network, just a direct linear regression for the policy and the critique. The idea is that if you do that, your estimated Q values must be very close from the true Q values, and deep neural networks are very slow learners. You need a lot of epochs to have the output catch up with the targets. So you may always have a bias here, and correcting by this is not going to help having an unbiased policy gradient. And the other problem is that this term can have a high variance. The ratio between how the learned policy takes an action and how the behavior policy takes the action can really take many values. So it will vary a lot, and we know that if we add a lot of variance to the policy gradient, then we will worsen the problem of sample complexity. That's why off-policy methods have a higher sample complexity, because this term has a high variance. So what we are going to do is try to limit the variance of the importance sampling term. Another thing that we will have to change is how we learn. So until now we have used gradient ascent or descent and the stochastic version, so that when we can estimate the policy gradient without the importance sampling term here, we just replace the expectation by samples of states and action, which must be IID, and we take the average of this term. So when we have the estimation, then we can apply that gradient to the weights using gradient ascent or some variants of it, RMS prop, Adam, whatever you want. So you're using the gradient to change your parameters, and what you in fact search is the smallest parameter change. It means you're using a learning rate as small as possible, so that the difference between the parameters is not too big. That produces the biggest change in the objective function. You want to change your weights just a little bit so that you get much more returns. And selecting this learning rate is very difficult, because if your learning rate is too small, then the networks will converge very slowly, and then the sample complexity will be high, because you're on policy. So we need to get a lot of samples, because you change your policy just a little bit every time. If you take a learning rate which is too high and you have a deep neural network, then the parameter update could totally destroy your policy and learning would be unstable. So what we want to do is to use another optimization method where the learning rate is going to adapt so that you are not taking the risk of instability in learning. So we are going to try to stay in what is called the trust region. We are going to change parameters as much as we can without increasing too much the objective function. That's kind of reversed way of thinking compared to gradient ascent. Here we want very small weight changes that decrease the loss a lot. And here we are going to make the opposite. Big weight changes that do not change the objective function too much. So why do we want that? So gradient descent uses gradient information, which is local. It's a view of the function in the neighborhood of the current parameters theta. If you take too big step in the direction of the gradient, you don't have information about the curvature of your function or what's happening far away from your parameters, because the gradient is only local to your current parameters. So if you imagine what you are trying to optimize is the altitude, you're trying to follow this path and go to the top of the mountain. And here that's the parameter space, so that's the position here in 2D. Your gradient is going in that direction. And if you take too big of a step, maybe you fall in a region where the returns become 0. That's true when your parameter space has a high curvature, so it's not some smooth linear function, it's something that is very steep. And that's the case when you have a deep neural network. It's always steep. In the neural computing course, you have seen examples of loss landscapes for neural network, and that's not a smooth quadratic function. It's always something very complex. And that explains why you may have policy collapse in DRL, because if you take too much of a step with your parameters, you may reach a policy which is totally bad. So you have to be really careful when you take the gradient, not to take too much of a step. But if you're too careful, you take a very small learning rate, you're going to make very small steps, and then you're not going to fall, but you're going to take a lot of iterations to reach the top of your function. And so that would add to the sample complexity, because if you're on policy, you need to sample new transitions every time. And so that will take really a long time. So our problem is that we want to go fast when it's safe and slow when it's not safe. So something depending on the curvature, on the second order derivatives, if you want, of the objective function. Because the problem when you are on policy is that once you reach in a region of the parameter space which corresponds to a very bad policy, you cannot recover, because you need to take new samples to change, and these new samples will be made by a bad policy. That's totally policy collapse, which is something that you observe very often in on-policy algorithms, but also off-policy. So that's an example I already showed when you train A2C, so an actor critique on-policy architecture. At the beginning of learning, your reward per episode on average is going to increase, then you reach a plateau, then you're back to your initial performance, so a random agent, and then you start from scratch, because your current policy will sample only bad transitions, so the progress will be slow again, and you have totally lost what you have learned before. That's a huge problem. What we actually intend to do is when my parameters are at this location, the only information I have is a gradient of the objective function, saying the returns are higher in this region. And I'm not going to just take 1% of this gradient, so proportionally to the learning rate. I'm going to search in a region around my current parameters. So I don't want to take too big of a step. Which change would increase the most the objective function? So I'm using, of course, information about the gradient, but I am also limiting the amplitude of my update to a certain region called the trust region, where I know that it's safe to move in this area, because here the curvature is not that big, it's a flat area. So if I stay in this circle, there will be no policy collapse. And I will take that update. So that changes quite a lot the optimization problem. Instead of having a first order derivative optimization, gradient descent, I look locally at the gradient and go as far as I can in this direction. Here I will still try to go in the direction of the gradient while keeping in a safe region where there's no policy collapse around my current parameters. So it's a constrained optimization problem. Still want to maximize the return of the policy on average, but keeping the policy as close as possible to what it was before, so that you avoid a policy collapse. And the tricky thing to do is that this region where we estimate that the policy is safe, the trust region, will change depending on the curvature of your loss function. If you're in a flat region, there's no risk making big steps. But if you're in a very steep region where the loss function changes a lot, then you will make much smaller steps. It's not something that you can do automatically with better optimizer like Adam, because it's only using the gradient information. It's not using second order information about the structure of the loss function. To do that, you need second order information. Not only the gradient, but the gradient of the gradient, so the Fisher information matrix. So our problem is now for a parameter update, for the current weights of the parameters, what is a safe region? What is a trust region? How big it is? And can we estimate what is the maximum change in the parameters that we can do in order to improve the objective function, but keeping safe?